Hey everybody, today I'm going to describe a project that I recently wrote in Python and uploaded to GitHub called Binary Search Experiment. I will, of course, link to the GitHub project in the YouTube description. And my audience today consists of people that know some basic Python. I'm going to assume that you have familiarity with at least one tree-based data structure, like a binary search tree. Um, that you know what a comparable data type is, although that you could probably follow along without knowing the precise definition of that, and that you know what a successor function does on an order set of values. And my goal for the project was to determine the optimal granularity of a search tree, and I implemented one to run some numbers on. And I don't claim that my implementation is like the best implementation of a search tree, but I think it's representative enough that you can kind of create a rule of thumb for what types of granularity work. And I'm going to cut right to the numbers to show what the outcome of my particular experiment was. And in my experiment, when I ran tests on a bunch of implementations, configuring them with slightly different chunk sizes, the best chunk size for me was a chunk size of 5, which in this case is 26.8 microseconds per trial, which beats everything else. And it also beats my reference implementation, which is just a binary search that's not nested. Now, I ran this experiment several times, and I will show you that I'm not making any strong claims here because the numbers like vary from run to run, and the numbers are obviously based on the hardware that I'm using, pretty typical hardware, as well as the way that I constructed the stress test. Now, I did use random numbers for the stress test, and I used about 1 million. I used 1.5 million values in the containers. So I think it was at least somewhat representative and enough to confirm my intuition about the chunk sizes, that you don't want it is actually helpful to have like more than 2 nodes per chunk, but you don't want to go overboard because then you lose the benefit of doing in an ideal implementation of a search tree. You literally do log n comparisons. When you start having a chunk size, then you get more a constant factor involved, which means you still have the same asymptotic complexity, but you are doing more searches per operation, especially in the worst case. So going back to the problem statement here, I have a large set of values that are orderable, and I want to create a container class for them. And I want to support not only search, but the successor function. And one thing to keep in mind here is that even though I don't implement it in this experiment, I have this idea that I eventually want my classes to support fast inserts and deletes. And that's the thing that precludes basically having a giant Python list. And so the rules of the game here were that the search and successor functions are only allowed to compare elements. They're not allowed to use any other properties of the concrete data type. But I do assume that the caller fulfills the contract that the elements are well ordered. For purpose of exercise, assume all values are distinct, at least for one element in the container. That's more for convenience than anything. And that I use O of n space for the data structure, and that's pretty easy to achieve in any reasonable data structure. And finally, I assume that there's a single thread of execution. Your choice of data structures in a multi-core environment would definitely require more analysis, and you would be able to achieve better results in the situations where you use multiple cores, obviously. So my solution essentially produced a recursive data structure. You have a nested search tree that includes a list of other nested search trees. Those lists could include yet other lists of nested search trees. And then finally, it's not turtles all the way down. You would eventually have a nested search container whose elements are simple search containers, and then the simple search containers would contain a list of elements of some sort of primitive order type like integers. And so like if you started off with a number of elements that whose could be factored into k times l times m times p, the structure might look like this. You have a single root of k nested search trees. Each of those include L nested search trees. So at that point, you have K times L nested search trees. I suppose it would really be K times L plus 1, but you get the idea. And then each of those nested search trees have contain M simple search containers per container. And then each of the simple search containers contain P integers. Now, when I did this, I strove to make the values P and M and L all equal to each other, and that's what the chunk size refers to down here in the output. But unless the number of elements in your overall container is a perfect fourth power of some integer, you eventually run out of elements. So sometimes these K and L values are actually less than the chunk size. I guess the next thing to do is just show you the overall structure of the code. So if I go into search.py, you'll see major block comments or doc strings that separate out the major components of the program. First is the simple search container, and it's really all this thing is just a glorified Python list, and the search algorithm is just a linear search. And the only special values that it returns are left and right, which means that if you are searching for this value other relative to the elements in the container, and that other is less than every single element in the container, we return left, and likewise for right. But you can, I think I explained that pretty well in the doc strings. And then the next class is the key class in this experiment. It's the nested search tree, and this is a container of containers. And the containers can either be a nested search tree itself or a simple search container. I do a bunch of testing just to make sure that my assumptions about the algorithm are correct. And then I add a binary searcher. And the binary searcher is used as a benchmark to make sure that my nested search tree is efficient in running in log n time. And of course, that assumes that I implemented the binary searcher correctly, but I follow the same algorithm that everybody follows. And also I measured that these things are fast on a population of like 1 million values. So I'm very confident that everything's basically running in logarithmic time. But this is the reference implementation. And then I have a function that actually constructs the overall object hierarchy. And this is a relatively complicated, although short, it's a relatively complicated function because I'm building a recursive data structure. So I'm actually like recursively building a list of recursive containers. I wouldn't dwell too much on that. And then finally, I run the stress tests, and you can see this at the bottom. And my stress test helper function basically gets passed in some sort of chunk size. I build up a searcher structure. I make some very basic assertions that the searcher that I build actually seems to be sane. And that's just me being paranoid, I suppose. And then I iterate over all the test numbers and collect data. So I think that's really it. As I said, I will put a link to this project in the description. I doubt this is going to evolve any further, but if it does, you'll be able to see it in the GitHub project. One thing that's not here yet, because of the chicken and egg principle, is there's no link to the YouTube video, but I am going to post a link, and that'll probably end up being right here. So what you're seeing when you view the video will look a little different. Anyway, thanks for listening.